I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will briefly discuss about one of the activation function, namely rectified linear unit, that we are calling it as the ReLU activation function. The ReLU activation function is one of the most widely used activation function in deep learning and neural networks. It plays an important role in helping neural networks learn complex patterns by introducing non-linearity. This is the main advantage of this model. And if you are taking the definition, the rectified linear unit is a simple yet powerful activation function used in neural networks, as I've said already. Its mathematical expression is given by ReLU of x is equal to max of 0, x, which means it outputs the input value directly if it is positive. Otherwise, its output is 0. This piecewise linear function introduces nonlinearity to the model, enabling neural networks to learn and represent complex patterns. Unlike other traditional activation functions like sigmoid or tanh that compress input into small range, ReLU allows for unbounded positive outputs, helping neurons stay active and propagate stronger signals during learning. And the graphical representation of this function is given by if the x value is greater than 0, ReLU of x is x, and is less than or equal to 0, the ReLU of x is equal to 0. The graphical representation will see the straight line. In this case, the straight line after above 0, the value will be increasing, and below 0, the value is equal to 0. That's why we are saying the straight line with the slope 1 for all positive x and flat at 0 for all negative. So all negative values. So if you are looking into this value, all negative, this value is equal to 0. That is what flat at 0. And expression, if you are looking into x is greater than 0, ReLU of x is whatever the x varies, it will be continuously varying. And for 0, the value is 0, flat. So the ReLU function is visually represented as a graph. How it has been represented, if you are looking into this graph, you can able to identify that the sharp transition at the origin. For input values greater than 0, the function increases linearly with a slope of 1. The slope is 1, forming a straight line that passes through the origin. For input values less than 0, less than or equal to 0, what is the value? The output is flat at 0. This graph is easy to interpret. It acts as a gate that allows positive inputs to pass through unchanged while blocking all non-positive values. This simplicity is not only visual but also computational, as the function can be quickly evaluated in large-scale models. Why we use a ReLU function, rectified linear unit? ReLU is preferred in many deep learning applications due to its efficiency and effectiveness. First, it is computationally inexpensive because it involves simple operations, just a maximum comparison, unlike sigmoid or tanh function that requires exponentiation. Second, the ReLU introduces sparsity in neural networks by outputting 0 for large portion of the input, especially during early training stages. This sparsity reduces computational load and makes the model more efficient. Third, the ReLU function is the ReLU helps to reduce the vanishing gradient problem commonly faced where it has been commonly faced with the sigmoid and the tanh functions, particularly in deep networks, because ReLU maintains a gradient of 1 for positive inputs. It allows for faster convergence and more stable learning in gradient-based optimization methods. ReLU in backpropagation. During the backpropagation process in neural networks, the derivative of the ReLU function plays an important role in updating weights. The derivative is 1 when the input is positive. The derivative is 1. Here, or ReLU dash. ReLU dash is 1 if x is greater than 0, if x is less than, and when the input is negative or 0, and when the input is positive, and 0 when the input is negative. This selective gradient flow ensures that only neurons with positive outputs contribute to learning while others remain inactive. While this feature helps in reducing unnecessary updates and noise in learning, it also has a downside. If a neuron continuously receives a negative input values, its gradient becomes 0 and it stops learning. This makes understanding ReLU's gradient behavior essential when designing and training deep networks. Limitations of ReLU. Despite its many advantages, ReLU is not without flaws. One major limitation is the dying ReLU. This is dying ReLU problem. A neuron is said to be dead if it is consistently outputs 0 and stops updating during training. This occurs when the neuron gets trapped in the negative input range due to poor weight initialization or high learning rates. Since the gradient is 0 for all positive inputs, these neurons effectively become inactive and contribute nothing to the learning process. If a significant portion of a network's neuron die, so what will happen? The model may underfit. It means model become underfit. We can say like this: underfit and fail to generalize well. This problem has motivated the development of several alternatives and variants to ReLU. What are all the variants of ReLU? To address the drawbacks of standard ReLU, particularly the dying neuron issue, I have said no in the previous slide. Dying ReLU, output gives 0, it will die. To address the drawback of standard ReLU, particularly the dying neuron issue, several variants have been proposed. Leaky ReLU. First one is the leaky ReLU modifies the original function by allowing small non-zero slope, typically 0.01 for negative inputs, ensuring that neurons still receive a gradient even when their input is negative. Next one is the parametric ReLU, goes a step further by learning the negative slope parameters during training, providing more flexibility and adaptability. And the third one is ReLU, exponential linear unit. We can call it as ReLU. Introduces an exponential curve for negative inputs, which can help the model converge faster and perform better. Another practical variant is ReLU 6. The fourth variant is ReLU 6, which clamps the output between 0 and 6 and is especially useful in mobile and low power devices. These variants maintain the core idea of ReLU while offering solutions to specific training issues. Where ReLU is used. ReLU is the default activation function in most modern deep learning architectures due to its simplicity and performance. It is heavily used in convolution neural networks, that we can call it as CNNs, convolution neural networks, for tasks such as image classification and object detection. The CNN mainly used in the image classification and object detection. Networks like AlexNet, VGGNet, this VGGNet and RESTnet rely on ReLU to maintain high training efficiency and accurate feature extraction. ReLU is also used in fully connected dense layer of feed-forward neural networks across various domains, including NLP, recommendation system, and speech recognition. Its widespread use is supported by empirical evidence showing that ReLU-based models often outperform those using other activation functions, especially in deep learning architecture. Coming into the summary, ReLU is a fundamental component of model neural networks. It introduces nonlinearity, improves computational efficiency, and supports faster training by mitigating vanishing gradient. These are all the advantages. However, its simplicity also leads to potential problems like neurons death, which can hinder learning if not addressed. Though variants like leaky ReLU and ELU, these issues can be mitigated while retaining the core advantages of original function. ReLU's ability to activate only a subset of neurons at any time encourages sparse and efficient representations, making it ideal for large and deep learning systems. Overall, mastering the use of ReLU and its variants is important for effective neural network design. Hope everyone understood about this ReLU function, activation function. The remaining things we'll discuss in the next lecture. Thank you.